everyone, today we will solve some numerical problems based on the discussion we have made in the last 4 classes. So, problem number 1. So, compound X has an ether water partition coefficient K soluble of 4. If 11 gram of compound X is dissolved in 100 ml of water, then how many grams of compound X will be in the organic layer after one extraction with 100 ml of ether. So, this is problem number 1 A, and then B, how many grams of compound X will be in the organic layer after 2 sequential extractions using 50 ml portions of ether each time, and C, which of the 2 extractions is more effective. So, we have to solve this problem, we will solve it, and as you see, this is a problem based on the distribution of organic compounds in aqueous and organic phase. When some pollutants are present in water, so that becomes in equilibrium with the biomass of the living organisms. So, there is some partition coefficient, and the concentration of organic phase is more than the concentration of the pollutants in the water phase, we have discussed in the previous class, and we have also seen that every time it is not possible to measure it. So, there are some standard process with specific organic solvent and water. So, the pollutants is used in the laboratory and it is separated in the 2 different phase, that is organic and aqueous phase, and then from that partition coefficient there are some relationship we find out the BCF, bioconcentration factor. So, similar concept we will be using here. So, what we will do, we have K, that is equal to concentration of that pollutant X in ether divided by C water, that is equal to K, it is given 4, and total mass is also given, that is equal to 11 gram. So, volume of the water is given, that is equal to 100 ml. So, for the case 1, say single stage extraction with 100 ml ether, what we will get? Let x gram of X get extracted into ether layer, and K equal to X divided by 100, this is the concentration, 100 x gram per 100 ml we have taken. So, gram per ml, x by 100 divided by 11 minus x, that is the amount of X present in the aqueous phase. So, 11 minus x divided by 100, that is the volume. So, concentration is equal to 11 minus x divided by 100. So, this concentration divided by this concentration, that is equal to K value as given here 4. So, by this expression, by solving X, we are getting 8.8 gram, 8.8 gram. So, 8.8 gram X gets extracted into the ether layer. So, how many is present in the aqueous phase? That is 11 minus 8.8, that is equal to 2.2 gram remaining in the water. So, first case A we are able to solve now, then case 2, case B. So, 2 parts with 50 ml ether each. So, we will be taking 50 ml of ether and we will mix this one the pollutants, and water we will also get, that is equal to 100 ml. So, then X divided by 50, that is the concentration of X in the organic phase, that is ether, and 100 ml water we have taken. So, that 11 minus x is going into the water. So, 11 minus x divided by 100, that is equal to again 4, because the constant is always K value is always constant. So, by solving x equal to 7.33 gram in ether. So, first 50 ml ether we are getting that 7.33 gram is coming. So, mass of X remaining in the water equal to 11 minus 7.33 equal to 3.67. Again we are adding 50 ml of ether with it, and then we are doing the separation by mixing, and then the X will be coming in the ether again. So, X by 50 in that case, that is equal to 3.67 minus x by 100 equal to 4. This will be, we may put it here x 1 also, x 1 and this can be x 1 x 2. So, then in this case solving x equal to 2.45 gram in ether. So, mass of x remaining in water equal to 3.67 minus 2.45, that is equal to 1.22 gram. So, total x extracted into this case into 2 ether steps, 2 separation steps using 50 ml ether in each step, that is equal to 7.33 in the first step plus second step is 2.45. So, it is being 9.78 gram. So, total 9.78 gram is separated into the organic phase. So, it leaves 1.22 gram in the water phase. So, that second part is also done. Now, third part. So, 250 ml extractions is superior to one single stage, because we see here in the second case using 2 steps consecutively only 1.22 gram x is remaining in the water, whereas in the previous case it was 2.22 gram x remaining in the water. So, now the problem is solved. See the next problem. So, problem number 2, here if a compound X has an octane-water partitioning coefficient of 130 and the concentration of X in lake water is 0.5 mg per liter, find approximate concentration of X in the animal at the bottom of all food chains in the lake. So, that we have to calculate. That means, in this case in the aquatic environment. So, pollutant is present in this water. So, in that case the pollutant will be in equilibrium with the zooplanktons and phytoplanktons and zooplanktons. So, phytoplanktons will be taken up by the living organism. So, we have to find out the X in the animal at the bottom of all food chains. Okay. So, that means, if we know the bioconcentration factor, then we can calculate it. So, that way here octane-water system is been given. So, in this octanol water system has been given. So, here we are seeing how we calculate the BCF. BCF we know the formula, the 0.79 into log of KOW minus 0.4, that is equal to 0.79 into log of 130 minus 0.4, 130 that is the partition coefficient KOW. So, this is one log, in this case 130, and this is a constant and this is also constant. So, this is our bioconcentration factor. So, bioconcentration factor in this case we are getting 18.62 liter per kg. So, by this formula we are getting bioconcentration factor 18.62 liter per kg, and by the concept or by the definition of bioconcentration factor we can get concentration of X in organic organisms mg per kg divided by what is this? This in the lake water, concentration of the pollutants in the lake water, that is 0.5 mg per liter. So, this equal to this BCF and this BCF value we are getting 18.62. So, we will put this value here, and by solving this expression we will get the value of X. So, what is this? Concentration of X in organism is equal to 9.31, that is equal to 18.62 into 0.5. So, 9.31 mg per kg. So, this is the concentration of X in the organism that we are asked to calculate, and now we are able to find out the value of it. Okay. So, now we will see problem number 3. So, here the statement is like this: consider a solution of ammonium sulphate prepared by dissolving 66 gram of the anhydrous compound in water and diluting to 1 liter. Then what is the concentration of the solution in gram per liter, moles per liter, equivalents per liter, gram per liter as sulphate and gram per liter as nitrogen. So, we have to calculate this as per the statement. Now, let us see. So, what we will see here, we have 66 gram per liter ammonium sulphate, then the gram formula weight of ammonium sulphate is equal to how much? 132 gram per mole, NH4 whole 2 SO4. So, if we take the atomic weight of each atoms and then sum it up. So, 132 gram per mole. So, molarity equal to how much? So, how many moles will be there in this 66 gram of material? So, that will be 66 gram per liter by 132 gram per mole, that we are getting 0.5 moles per liter, or the strength is 0.5 molar. So, with respect to molar, so which we are asked in the question number B, moles per liter, that is molar, moles per liter, and that was gram per liter. So, we are able to find out, and then third is your equivalence per liter. So, what we will do in this case, equivalence per liter, that is normality. So, that moles, how much molar strength into 2 equivalents per mole, because your ammonium sulphate has 2 valency. So, without any specific information regarding the use of this solution, one might simply presume that either the sulphate group or the ammonium group will be the reacting species, and in either case Z would be equal to 2 product of the oxidation state times the number of groups, that we know, and then normality is becoming this one, or that is equal to base. We are getting 1 equivalent per liter or 1.0 normal. N by 1 we can say, somewhere we can n by 10, n by 100. So, in this case it is we are getting n by 1 or n. Then for question number part D, let us see the molecular weight of sulphate. So, SO4 32 plus 4 into 16, so 96 gram per mole, and the molarity of sulphate is, how we will get it then, 0.5 moles, this is the molar strength we have ammonium sulphate. Now, I have to convert in terms of sulphate. So, we have to multiply it 1 mole sulphate by mole of ammonium sulphate. So, in this case we are getting 0.5 moles sulphate per liter, because 1 mole sulphate we are getting from 1 mole of ammonium sulphate, and hence mass per liter, that is equal to molarity into molecular weight. So, 0.0 moles per liter and molecular weight is equal to 96 gram sulphate per moles of sulphate, that we know. So, that is equal to 48 gram sulphate per liter. So, this much of sulphate is present in it. For part E, the molecular weight of nitrogen we know that is 14. So, molarity of nitrogen is equal to how much? So, we have 0.5 moles ammonium sulphate. So, 1 ammonium sulphate having 2 nitrogen. So, 2 moles ammonium per mole of ammonium sulphate. So, we will be multiplying it with this. So, 1 mole nitrogen per liter. Therefore, mass per liter equal to molarity into molecular weight. So, 1 into 14 gram per n. So, we are getting here 14 gram nitrogen per liter, or 14 gram ammoniacal nitrogen per liter we can say. So, that way we can solve the problem. Now, we see the problem number 4. The statement is, the octanol water partition coefficient Kw of a pesticide is 3 lakhs. Calculate the bioconcentration factor of it in fish to water. If the concentration of the pesticide in water is 2 ppb, what will be the concentration of it in fish? So, again similar to that problem we have discussed just before few minutes. So, then here log bioconcentration factor equal to the empirical formula we will be using 0.79 into log Kw minus 0.4. So, BCF equal to here 0.79 into 33 lakhs, we will put it here. So, log of 3 lakhs minus 0.4, that is equal to 8451.344. So, concentration of pesticide in fish, we will be using the definition of it. So, what is the concentration? 2 pp, that will be multiplied these times. So, that will be this 16,902.69 ppb. Okay. So, now we will come to the next problem. So, problem number 5, the statement is, how much solid waste is generated in ton per day from Roorkee and Meerut if their populations are 1 lakh and 50 lakhs respectively. So, this problem is based on the pollution generation capacity per capita waste solid waste generation capacity. So, Roorkee 1 lakhs and this is 15 lakhs Meerut. So, if we compare, one is small city, another is your medium town. So, as we have discussed in the previous class. So, here we are getting the small town Roorkee. So, solid waste generation gram per day, we know that 100 to 200 gram per day per capita. So, if we multiply the population with this rate of production, so we will be getting the solid waste generation per day. So, in this case 1 lakhs into 100 or 200. So, we will be getting here this in gram. So, we will convert it into kg by dividing it by 1000 and to ton by dividing again by 1000. So, we will be getting 10 ton per day to 20 ton per day. So, this is the waste generation in Roorkee per day. And for Meerut, this value will change, because we know that for medium city per capita waste generation is different from that of the small city, and it is 300 to 400 gram per person per day. So, if we multiply with the population, that is 15 lakhs. So, 15 lakhs into 300 or 400 divided by, again have to divide it by 1000 for conversion of gram to kg, and again 1000 from kg to ton. So, we will be getting a 450 ton per day to 600 ton per day. So, now we are able to find out the waste generated in these two city per day. So, the statement of the next problem is, when chlorine is used for disinfection of drinking water, chloroform can be produced by the reaction of chlorine with residual organics in the water. Estimate the ingestion intake rate for non carcinogenic effects on an adult resident in a home receiving tap water with an average chloroform concentration of 65 microgram per liter. What is the risk? Oral RFD of chloroform is 0.010 mg per kg day. So, now we have to solve it. Okay. So, this is a problem related to the risk assessment, which we have discussed in the previous class, and we had one expression as given here, I is equal to C into R I into E f into E d by B w into A t, which we have discussed in the previous class. Now, we will find out these values and put these values here to get the value of this I, which is nothing but the ingestion intake, and here C is the concentration. So, 0.065, this is microgram per liter. So, we are putting it here 0.065 mg per liter, and then what is the intake, that is the per day water intake is 2 liter per day, that is R I, and E f is equal to the frequency 350 days per year, and then duration is 30 years, because it is non carcinogenic effect. So, as per the EPA guidelines in the previous class we have discussed. So, those values we have considered, and divided by B w, that is body mass weight. So, that is equal to 70 kg for an adult and 365 day per year into 30 years for 30 years. So, total AT is equal to 365 day per year into 30 years. So, then by this expression we are getting 1.8 into 10 to the minus 3 mg per kg per day. So, this part is now over, we are able to find out the ingestion intake rate, but we have to find out the risk as well. So, how can we find out the risk? So, risk is equal to, we know that relationship hazardous quotient, risk can be calculated on the basis of hazardous quotient. So, then HQ, so that is equal to I by RDF as per definition. So, this intake is 1.8 into 10 to the minus 3 and here 0.010 mg per kg day. So, this equal to, we are getting that HQ is less than 1, in this case it is less than 1, and we conclude that this level of chloroform concentration constitutes an acceptable risk. So, this risk is not much, it is acceptable risk, because it is less than 1. So, when the HQ is less than 1, then the concentration is acceptable. Okay. So, another question, that is problem number 6. The statement is, if benzene, a known carcinogen, is found in air at a constant concentration of 1 microgram per meter cube, calculate the risk for exposure to this benzene for an average adult who inhales 20 meter cube per day with 50% absorption for a lifetime. benzene slope factor is 0.015 mg per kg per day. So, this is again another problem related to the risk analysis, and we have this expression I equal to C into R I E F into E D by B W into A T, and this is a carcinogenic effect. This may have carcinogenic effect. So, risk we can calculate with the help of SF, that is your slope factor, and what is that? That is lifetime cancer risk LCR, that is equal to I into SF. So, this we did not mention in the previous class, but the lifetime cancer risk is equal to I into SF, that is intake into slope factor, that we can calculate, and if the value is 10 to the power minus 6, then it is acceptable, or less than this, then it is acceptable threshold. If it is more than that, it is not acceptable. So, then now let us see the value of I. The I is equal to, so C is equal to how much? 0.50 into 1 microgram per meter cube into 1 mg per 1000 microgram. So, the conversion of unit, and then 20 meter cube per day, because 20 meter cube per day we are taking, and your 350 day per year and 70 years, because it is your carcinogenic acute effect. So, 70 kg in 365 day per year into 70 years we are getting. So, why this is? Because 1 microgram, if we want to convert it into mg, so that will be divided by 1000, but 50% absorptions of a lifetime. So, that will be your this one, and then divided by this. So, we are getting this mg per kg per day. Then LCR is equal to I into SF. So, I we are getting 1.37 into 10 to the minus 4, and so that into, and we have to get the value of SF. SF value is given 0.015. So, we will multiply it, and we are getting 2.06 into 10 to the minus 6, but this is the threshold value 10 to the minus 6, but here the value is more 2.06 into 10 to the minus 6. So, this exceeds the 10 to the minus 6 limit. So, this risk is unacceptable. Okay. So, that will be hazardous for the health. Okay. So, up to this, in this class, now we are able to solve 6 numerical problems based on our previous 4 classes. Thank you for your patience.